This video demonstrates GscalerCloud. In stage 1, we will demonstrate using small graphs. GscalerCloud accepts three types of inputs. The first type of input allows users to manually draw graphs. The second type of input allows users to input the adjacency matrix, and the third and the best way allows users to directly upload the edge list. In the manual draw option, users can create nodes by clicking on the blank space. To draw edges, drag the mouse from the source node to the target node. To delete nodes or edges, select and press the delete key. After drawing the graph, to download the edge list, users can click on the Download Edge List button. This file can then be uploaded onto the main page for the purpose of scaling. After uploading the edge list file, the edge size and the node size of the original graph are displayed. For this demonstration, we are using a graph which has 6 nodes and 7 edges. Suppose the user wants the scaled graph to have 14 nodes and 13 edges. The user is required to enter the scaled edge size as 13 and the scaled node size as 14 and click on the Submit button to rescale the graph. Gscaler rescales the graph very quickly. In this case, rescaling is done in less than 0.1 seconds. The user can then download the scaled graph file or can compare the similarity between the original and the scaled graph online. The parameters on which similarity comparison are performed are in degree, out degree, strongly connected component, effective diameter and shortest path, average clustering coefficient. Users also have the option to visualize the original and scaled graphs side by side. In our example, both the original and the scaled graphs are binary graphs, where the original graph is unbalanced. For both the original and scaled graphs, it can be seen that the left branch has a greater height than the right one. Stage 2 of our demonstration, we will be scaling with large graphs. For this purpose, we use /dot from Stanford's network collection. The user uploads the /dot edgelist file to the server. The server analyzes it and displays the original edge size and node size. For the scaled graph, we enter the scaled edge size as 33,000 and the scaled node size as 4,200 and submit it. GscalerCloud generates the graph within seconds. Visualization is not allowed for large graphs. However, users can compare the in-degree distribution of the original and the scaled graphs. The x-axis represents the in-degree number, and the y-axis represents the number of nodes having that in-degree. We allow users to zoom in by replotting the graph in the range specified by the user. Suppose the user wants to replot in the range 0 to 100. The user enters the lower bound as 0 and the upper bound as 100 and clicks the replot button to replot the graph. If the user wants to further zoom in, suppose he wants to view the graph between the range 1 to 20, the user will enter 1 as his lower bound and 20 as his upper bound and click replot again. Out degree works in the same way as in degree, so we skip its explanation. For strongly connected component, we see that both graphs have a large number of strongly connected components. For the original graph, the largest strongly connected component comprises of 91% of the nodes, and the scaled graph, the largest strongly connected component comprises of 92% of the nodes. Users can also choose to view the effective diameter and the average shortest path. The effective diameter for both the original and the scaled graph is 5 for the /dot dataset. For the average shortest path length, for the original graph, it is 3.7 and for the scale graph, it is 3.4, which is pretty close. For the average clustering coefficient, the original graph has a clustering coefficient of 0.052 and the scale graph has a clustering coefficient of 0.056. They only differ by 0.004, which is very close. With this, we conclude the demonstration of GscalerCloud.